Okay, so important, two important equation for fracture. One is for ductile, one is for brittle material. Okay. So we continue topic on brittle. So how brittle fracture happen? It is when you have a defect or imperfection happen in the metal, and all these defect that we don't want, all these undesirable defect. What are the undesirable defect? Is all these. We have a crack, we have porosity. Porosity means you have a hole. We have indivisible grain flow, poor microstructure, and so on. So for brittle fracture, it consistently initiate at the defect location or stress razor, regardless of the cause of the formation defect. So for brittle, they are very sensitive to the crack size. They are very sensitive to that crack, right? So for example, the one you see on this diagram, if you see the pattern here, you actually can predict how the crack was formed. You look at the pattern, you follow like a river stream, you walk upstream. So you see there's a line here, a hairline. You lock hairline, then this one is like hairline. So this is the area where the crack or fracture is happening. You just follow like a river, you follow upstream. Then this is the area where the fracture start to happen. This area is called the there's a stress razor is here, and we try to avoid sharp corner in all our engineering design. Right? It depends on operation. Sometimes sharp corner they are good, but sometimes they are bad, especially those transmission power transmission area. Sharp corner is very bad for because they are the area where crack will happen. The rest you read, You're familiar with this diagram in your lab experiment. So how do we test the fracture of metals? We define our toughness of metals using impact test. We have impact toughness. What is impact toughness? Is the amount of energy a material can absorb before fracturing under dynamic loading condition. What is dynamic loading? You load, then you load again, then you load again. Okay. Opposite of dynamic is static loading. Static loading means you only one time. Not one time, then you stop. Okay. So we have this one in the lab. But unfortunately, it need to send for maintenance. Right. So I'll show you the sample. So the sample that you've seen in the lab is the V-notch specimen. So this hammer, if you observe the equipment we have under in our lab, you just raise the hammer, and then there's a reading here. There's a scale here. Our instrument is not at the top. Our instrument is at the somewhere in the middle. Right. Then there's energy absorbed and so on. It was calibrated to a certain value. Okay. So if you look carefully, there is a dimension for the specimen. So how we set up? This is the sample that you've seen in the lab, the red color one. So you put the sample on the height of the notch. So let's say this is the notch. So you just slot it in. In our lab, the slot was inside. You cannot see, right? So In the middle, this one, you just put the sample slot in, then you will lock the sample like this. Okay, so you have a EZOT and Chappie setup. We have two kind of setup. One is EZOT. EZOT means vertical. Then Chappie is horizontal. Right? So this one you knock from the top, then this one will bend. This sample will bend, and it will crack from this edge. Another one is you from the back. From the back, this one will turn like that. It will open up like that. Okay. So you have EZOT and impact test. Look at the name, and then that is the way they hit the sample. Okay. IZOT means you look at the I, the vertical, the capital I means it's a straight standing. Chappie is lying on the flat. Okay, so these are the sample of the V0 specimen. Okay. So this is energy, absorb, and temperature. So different material have different value. Okay, so this graph, how you read this graph? Energy versus temperature. On the left-hand axis, energy in joule, temperature x-axis in Celsius. On the far right is the shear factor percentage here, right? So there is a formula to calculate shear factor. I haven't shown you. On the top is Fahrenheit. So you can see A and B. So curve A is for impact energy. B is for percentage of shear factor. So if you want to read energy, you extract information from the blue line. If you want to extract information for the shear factor, you read the red line. Okay. Okay. Next, we look at ductile to brittle transition temperature. So at low temperature, high straight state, fast loading rate, they will all cause a ductile material to behave in a brittle manner. So just now, before the break, we mentioned two very important factors in fracture: temperature and the rate of your strain loading. Here, if you change the temperature low, give it very high stress, and do it very fast or fast loading rate, then you can change ductile fracture into transition into brittle fracture. So here you look at the diagram, is lying flat or lying in a horizontal manner. So this experiment is called Chappie V0 testing. If it's standing, is a IZOT or EZOT impact test. Okay. So yeah. Okay. Right. The one that you see in the lab under there is that it conducted at the 15 degrees C aircon room temperature. But if you want to conduct like doing as your FYP, then you need to put the whole experiment in the furnace or refrigerator unit. There's a range there so that you get this graph. Temperature versus energy. Okay, so put all this in your experiment lab report. Okay, go and find what is impact test. What are the graph related to that sample? So your lab report for experiment 1 will be more on theory. Okay. Ductile to brittle transition, in my slide I use capital D, capital B, and T. What factor that affect the DBT temperature composition? heat treatment and processing. Heat treatment and processing, actually, they are the same area. Heat treatment is why you need to do heat treatment because you want to make the material become stronger. Processing is how you do it, all right? In one of the chapter before this, we have done one chapter on the processing. You hammer it, you roll it, you pull it, that one, okay? So as you can see on the diagram here, energy versus energy, you have y-axis and two y-axis. On the left is imperial unit, on the right is joule. Temperature, now the temperature above is Celsius, below is Fahrenheit. So when you read graph, refer to the correct axis. For engineering material, the graph is sometimes not follow the normal sequence, the normal setup for the graph. Just be careful. Okay. Okay, the rest you read. Okay, the rest you read. This is the percentage of carbon. As you raise more carbon or you reduce the carbon, the energy. You see this one? Let's say we capture two line, 50% carbon and maybe 22%. So let's check at frozen temperature. Let's say frozen, freezing temperature 0 degree. The energy absorbed is very, very low, maybe 10 joule. 50, 10, about 10 if you have 50% carbon. Then 22% is a bit higher, so 0 you go up, move to the left, will be about 70 or 80 joule. This is another graph, also percentage of carbon, how they affect the impact energy versus temperature. Okay, I show you before we start the class. This the Titanic happened because it changed from ductile to brittle transition because of the cold environment. As you can see from this graph, let's say if the Titanic, I don't know the percentage of Titanic material, let's just assume. So let's say you take a 50%, 0.5% carbon. You at the percentage of sea, let's say the sea water at normal water, let's say Malaysia water, maybe 30 degree. So 30 degree, you see the energy is about 30 joule. But when you go to Arctic or those North Arctic area, so it will be go to negative one. So negative area, you see, is much lower than the energy. So it will become ductile, you drop to brittle. Okay. So tomorrow you have a material lab. Go to the fluid lab, you know the door, fluid lab. Go in, and then, or you can go in from the fab lab also. Then from lab there is a microscope there. So we will wait you there. So there you will see what is perlite, what is ferrite tomorrow. You see the color of the sample. Okay. This is another illustration of the just now. You have done the calculation. So this is another review of how to calculate the fracture cases. So again, your crack can be two cases, one at the side, one at the center. It can be two cases. But the calculation still same. We are using the single A, not 2A. We are using the single A in our calculation. So here. So on the left, A or B is actually the same. Both of them subject to tensile loading. Uniaxial tension. Uni means one direction tension. So if you plot the graph, y versus x, x is the distance from the side or from the origin or from the, right? So y is your stress. So you have y max, stress max, then U and nominal. So before the break, we give you one equation that link stress max and nominal, that you can find the stress concentrator constant value, the KT. So from here, you able to find, this is the crack tip. So all this area, this is max, this is max, this is max. Okay, the crack tip, all the tip, they give you maximum stress. Okay. By looking at the picture, what is happening to the object? A, pulling both sides, the crack go this direction. You pull, but go this direction. Then this one also shear. This is called shear loading. The force and the surface go parallel, it becomes shear. But this one, different direction, also shear, because it's parallel to the surface. So it will like tearing the thing. And this one, force go opposite direction, but still you see the crack propagation also go in this direction. Okay. So there are three modes of surface crack. There are three modes. First, mode 1 is the opening. It's a normal, you try to tear something. So this is mode 1. Mode 1, crack of mode 1 crack. So if you run simulation using finite element analysis or ANSYS software, you can define what mode you want to simulate. So mode 1, mode 2 is a sliding mode. Mode 3 is tearing mode. Mode 1 opening, mode 2 is sliding, mode 3 is tearing. Okay, so there are three modes, three modes for under fracture. What else? Okay, so the next one is that for metal plate, for mode 1 testing, mode 1 testing is this one. Okay, mode 2, mode 3. So since we already introduced you what is the mode, so in your test later, final exam or test 2, we will not, we will, you might not see any diagram anymore. We will tell you what is the mode of the test or what is the mode of motion. You need to draw the diagram out and then you do analysis. So for mode 1, okay, mode 1 is opening, this one is opening, this one. So by experiment, for the case of unit tension, unit plate containing edge or internal crack, mode 1 testing, it open up like that. So what is mode 1? Mode 1 is like a crocodile mouth lah, crocodile mouth. So you can see if at the edge, you pull at the edge here, so you like open up like that. So it's a mode 1. So mode 1, you use this equation. What is K1? K1 is the stress intensity factor, the K. You use a constant value Y times the stress applied, nominal stress. This is what you apply to the object. Square root of your pi and A. So the K beside there, there's a 1 there. It means is in the mode 1. Okay, it's a mode 1 means there is a opening like a crocodile mouth. Okay. In the test, if Y is not given, assume 1. Okay, in test or final exam, if Y value is not given, assume 1. You just in your answer, you say assume Y equal to 1. Then you proceed with your calculation. Then you modify a little bit this equation, the mode 1 stress intensity factor. You modify a little bit. If you want to find the critical value of stress value, just now, you just modify a little bit. When it become a critical stress intensity factor, you change the stress value. You change the stress value to become fracture stress. Stress that make it fracture. Right? Means K1C, 1 means mode 1, C means critical. When you use the word critical means it already failed already. So you're using the failure, the fracture stress or the failure stress. We're still using the A, not 2A. We're still using the A with the length of the crack. Oh, sorry, half length of the internal crack. Okay. The unit will be megapascal square root meter. The unit megapascal square root meter. This one, if the answer is 3 marks, unit will cost you 50%, 1.5 marks. So if you do not write any unit, you only get 50% of the answer. Okay, so be careful on the unit. Okay. This is another more detailed diagram. This is a mode 1 fracture for testing. It's open like a crocodile mouth. So this is a compact type. Okay, so on the left, you see there's a sample diagram. This is a sample of the cracking, and then you see there's a 2 hole here. 2 hole here, you push 2 steel at this location, and then you try to open this mouth. The instrument will pull these 2 blue color area side by side. So one will go up, one will go down. Okay. Then you need to measure the A here, the W here. What else? B here, and there's a calculation. Okay, the rest you read, Okay. So this is a plane strain coordinate. Okay, this one you read lah. Not important. The B here, when you prepare the sample, the B thickness should be 2.5 K1C, K mode 1 critical. You use the previous equation you see previous slides, divided by the U strength. Divided by the U strength. U strength square. Okay. You will see this table in your coming test. So this table give you material. K1C means mode 1 critical value, and the U strength. This table, the purpose of giving you table is this to apply this equation. You see U strength, K1C, you apply the previous equation, you did this one. So what is missing? If the value is given, this one. Fracture stress is missing. Or fracture stress is missing, A also can be missing. It will ask you to predict the A or predict the F. So this table just read carefully. We are using unit SI. Use the megapascal square root meter and megapascal. Okay. You have a quick comparison. Let's say we take aluminium 2024. The KIC is 26 something. But you try to look at the titanium. Titanium very hard material. The KIC is 55. So it means the harder the material, the higher the KIC. Same with the U. The U strength also very high. Okay. So low fracture toughness value, materials show little plastic deformation before fracture, have relatively low fracture toughness, and tends to be more brittle, where those with higher KIC value are more ductile. Okay. So this is a descriptive question that asks you to explain after you calculate the value. I give you a table, then you predict whether this material is brittle or is ductile. You predict, huh? This is another table, same. You're seeing U strength and KIC, but the column is flipped. Column is flipped, but more material name is here. Again, use megapascal square root meter column. You will see Appendix B in your canvas. There's a table B.5 inside there. Go get familiar with table B.5. Okay, go into Canvas, go and download Appendix B, and then go and see what table B.5 look like. Okay, don't panic in test, huh? Okay. And I put in my slide also already. I give you hints that exam or test will use Appendix B material. Okay. Okay, let's look at example 2. Then I think we can call it a day. Okay. Right. Now, you look at the question. A structure plate component and of an engineering design must support 207 megapascal. Again, change all the giga, mega, micron into 10 power something. This one is 10 power 6. Okay. In tension. So tension means pulling both sides. And just now, we only teach you mode 1 failure, K1C. If aluminum alloy 2024, and in the table just now, I highlight just now, used for this application, what is the largest internal flaw size? This actually asks you to find the A value. Flaw size means the crack. For this material can support, use Y equal 1. Again, if the question do not mention Y, you just, in your answer, you assume Y equal 1. Okay. You call out K1C, Y equal to failure stress, square root pi A. Then you go to the table. You go to the table. Of course, in test or final exam, you will see Appendix B graph table. Okay, so this one, you look at aluminium 2024 T851. So you go to T851. You copy the value of K1C and the U strength here. You copy these two, then stand by for calculation. You rearrange this equation to find the A because the question asks you largest internal flaw size. Actually, it's a A. You rearrange, you pull the Y to left, stress failure, stress to the left, square root, pull, it becomes square. Right? So K1C you have U. U is U is given. Okay, U is given. U, it means this one, the failure is, in this question, is the customer requirement. You have a value maximum that it can support. Okay, so here you put the stress failure as 207 for stress failure. KIC, you read from the graph, from the table. Remember to put in unit, yeah? Megapascal, square root meter, megapascal. So we can cancel Pascal, Pascal, right? Cancel Pascal, megapascal, megapascal, cancel. Bracket square, square and square root cancel. You reach M. This one 1 over pi is a constant value. So your A is in meter. 0.00518 meter. Okay, or 5 mm. 5.18 mm. Okay. So the largest internal crack size of this plate can support is 2A. So this one you multiply 2, it becomes 10. Okay. So again, crack it can be 2. Crack it can be 2 scenario. One is at the side one. One is at the center. So this is A. This is 2A. But for all calculation, we use A. Okay. So he asks you what? What is the largest internal floor size? This is internal. Okay. It depends on question. Sometimes the question will give you directly the V notch, the V naught sample size. Meaning, it will tell you, give you a scenario. Now you're conducting an experiment. You're given a V notch sample. And you're having a impact test. So if the question is a V naught sample, either is a IZOT or Chappie, same. So the sample you know is at the side. So when you give your answer, the answer is in A and not 2A. This question, it mentioned internal floor. So that's why you need to give the answer 2A. Okay. Okay, the rest we continue next lecture.